Hello and welcome to our next lecture on space-time codes. Let us start with a brief outline of today's talk. We will start with the concept of space-time codes. We had originally looked at multi-antenna systems and we would justify the use of that in the context of space-time codes. Then we would look at the classic Alamouti Code. Then we will talk about diversity and diversity gains, plus we will have some examples to illustrate the concepts. So, let us see what we have done in the previous lecture. We have looked at TCM schemes, looked at combined coding and modulation, defined free distance, design rules, performance evaluations, and finally, we went over to space-time trellis codes, where we started using two antennas. So, that was a logical extension of space trellis coded modulation going on to space-time trellis code. In today's lecture, we would look at the space-time block codes, where we do not have so to say trellis to help us encode the sequences. But before we do so, we start with a quick motivation. We start with wireless channels, because this is where we will be using space-time codes frequently. So, the inherent characteristic of any wireless channel is multipath propagation. We have seen this before and this leads to signal fading. Now, one of the ways, actually an easy way to improve the capacity of wireless channel is to use multiple antennas at the transmitter and receivers. Okay. So, multiple antennas can provide several things, including the diversity gain that we talked about in the last class. But the problem is that the receiver could be your handset and you do not have enough space to put multiple antennas. So, it is logical to put more number of antennas at the base station. So, what we would like to do is we would have to also have a minimum separation between the antenna elements for them to be fading relatively independently. So, the requirement of spacing between antenna elements and the space available on the receiver handset restricts putting multiple number of antenna elements at the receiver end, but from the base station's perspective this can easily be done. So, as we mentioned, not practical to deploy multiple antennas at the receiver, but on the other hand base stations can easily accommodate multiple antennas. So, this is the basic premise with which we will start. We will have multiple antennas at the transmit side. So, we are going to look at multi input single output or MISO systems. Now, space-time coding basically allows different symbols to be sent from the different antenna elements in different time slots. So, we have already looked at space-time trellis codes STTC as a natural extension of trellis coded modulation, and today we would delve into space-time block codes. That is the subject for today. Now, let us start with the anatomy of a space-time block codes. Shortly we will discuss the details. So, we are talking about STBC space-time block codes. Let us start from the first block, the information source. And this source is generating enough bits, and what we do is we take 2 bits at a time, and in general we can start with B bits at a time. So, if you club it into 2 B bits, then we can look at a signal constellation with 2 B symbols. So, let us quickly look at it here. So, the source will generate 2 B, which is nothing but B and B. Now, what we do is we have a constellation, this is predefined. This constellation has a certain number of points in the constellation diagram. So, suppose we choose any constellation and in this there are 2 raised power b points. So, for the first b, I will go ahead and pick any one point, and for the second b, I will go ahead and pick another point, because b bits will correspond to any one of points in the constellation diagram. And once we pick up these 2 points, then we say that this is your S1 and this one is your S2. So, we have a pair S1 S2 pair. This pair has to be sent to the space time encoder. So, this is a space time encoder, and this guy has 2 antenna elements. And what do these 2 antenna elements do? Well, they have got these 2 symbols S1 and S2. So, they will take S1 and S2 and transmit it out. But we observed that the receiver may not have the luxury of multiple antennas. So, we have only a single antenna at the receiver, right, and the receiver receives S1 and S2 simultaneously, plus there will be some noise also coming. So, we will have N1 and N2 for the 2 signals S1 and S2, and this will then be fed to your channel estimator, right. And of course, I would also have, based on the channel estimation, a combiner. So, I will get the estimates of the channels. Now, what are these channels? Well, we can represent it as H1 and H2, these are complex. So, these represent my channel gains, all right. So, these are complex numbers, and the signal S1 gets multiplied with H1 and gets added with noise N1, and similarly S2 gets multiplied by H2 and then gets added with N2. So, the estimates of these two, H1 hat and H2 hat, have to be given to the combiner. And here after that we will take this for maximum likelihood decoding. So, if we go and look at the slides once again, we have the same concept exemplified here. You have this information source, you take 2 B bits at a time, separate out these 2 B bits into B bits and B bits, and each one picks up a point in the constellation diagram. So, I have a pair S1 and S2, which is fed to the space time encoder. Now, this antenna spacing is providing the space. We have not talked about the time part yet. So, we have now the time slot. So, in time slot 1, we send out S1 and S2. So, if you see there is a matrix, right, and if you want to look at this as a time axis, then this there will be symbols along this and this will be the space. So, this is corresponding to antenna element 1 and S2 corresponds to antenna element 2. But what we do is we then also do something more interesting in the next time slot. So, this is the axis, and I already have S2 and S1 available with me, and they are complex because they are coming from a constellation diagram. So, they have a amplitude and phase. I do a simple computation, I do minus S2 star for example and S1 star. So, I take this complex conjugate, multiply with a negative, and again load it this guy onto antenna element 1 and the second person onto antenna element 2 and retransmit. So, please note this 2 B bits resulted in the transmission of S1 and S2 from antenna elements 1 and 2 in the first time slot. And then now we have not taken any more bits. In the second time slot, what we have done is we have sent something different based on S1 and S2. So, that is the rule. So, regardless of what S1 and S2 are, the next two symbols to be transmitted simultaneously will be minus S2 star and S1 star. This is just an example. This is a strategy. This is my coding strategy, and therefore, this can represent my space time block code. Why this will work, how good is it, why are we doing it in this, all of these questions will be answered in the subsequent slide. But the method is pretty easy, it is mechanical, but the beauty lies in the decoding part. So, let us go on and see what really is the gain that we get from doing this kind of encoding. So, let us look at a simple example. Consider a wireless system with 2 transmit antennas and 1 receive antennas. So, these 2 transmit antennas could very well be seated on the base station, and the receive antenna is your handset. And we have to have some constellation diagram, signal constellation available to us. It could be MPSK, MQAM, what have you, right. And this constellation could be real or complex. Okay. So, there is no restriction that it has to be complex. Now, we will transmit B bits per cycle, right, and we will use a modulation scheme that maps one symbol from the constellation with 2 raised to B symbols, and the output will be x1, x2. And as we mentioned, this encoding takes 2 time slots, right, and we have this coding strategy. So, this particular way of coding has a name based on the person who first proposed it. It is called the Alamouti Code, and this is the depiction for the Alamouti Code. So, if you have this as the coding strategy, then the code word matrix C, as we just now observed, could be written as follows: S1 S2 minus S2 star S1. Okay. So, this method of doing space time coding can be expressed in the form of a table. Here on this axis we have the space, antenna 1 and antenna 2, they are spatially apart. Here we have the time period 1 and time period 2. So, this is the time axis, and as we mentioned in the first time slot, we use antenna 1 to send out S1 and use antenna 2 to send out S2. And then in time period 2, we do minus S2 star and S1 star, load them onto the antennas and transmit. So, this is in a nutshell the depiction of the Alamouti Code. Okay. So far it is pretty easy, but now let us make some interesting observations. Why has it been chosen like this? What is so great about putting a minus S2 star and S1 star here? So, the first observation is that x Hermitian x, where x was given by this, okay. This is just showing a general coding strategy, and if the exam symbols were S1 and S2, then coding strategy will put S1 and S2 in the place of x1 and x2. So, x represents the code and this is the code word matrix. So, x Hermitian x is x1 squared plus x2 squared, right, absolute value squared, into this identity matrix. Now, as we mentioned, after we transmit the symbols, they go through the wireless channel. So, the symbol S1 gets a channel gain H1, it is complex, can be represented easily by alpha 1 e raised by j phi 1, and H2 is the channel gain encountered by symbol S2, equal to alpha 2 e raised to the power minus j phi 2. So, let us make some more assumptions. It is assumed that the feeding channel coefficients h 1 and h 2 are constant across two consecutive symbol periods. It is not a bad assumption. At the data rates we have, the symbol rates that we employ, the channel does not change significantly between the two time slots. Okay? So, is that a fair assumption? Yes, it is a fair assumption. Now, the received signal over the first two symbol period denoted by R 1 can be represented as R 1 is H 1 S 1 plus H 2 S 2 plus N 1. Now, if you look at the second symbol period, right. So, this is time slot 1, because in the time slot 1 both transmit antennas are transmitting simultaneously. So, transmit antenna 1 sends S 1, transmit antenna 2 sends S 2, both get multiplied by the respective channel gains, and in the first time slot I have got the noise N 1, and similarly in the second time slot I have got noise N 2. But what has happened for the next time slot, the received signal that I get in the second time slot is I sent out from antenna 1 minus S 2 star and from antenna 2 S 1 star. So, this should be S 1 star, and we have this R 1 and R 2. Now, the aim of the receiver is to extract the transmitted symbols x 1 and x 2 from R 1 and R 2, that is the aim. So, the receiver requires some kind of a combining scheme. So, we have a strategy in place based on the channel estimates. So, we assume that we have some knowledge about the channel gains H 1 and H 2, and the combining scheme R 1 tilde is H 1 star R 1 plus H 2 R 2 star, and R 2 tilde is equal to H 2 star R 1 minus H 1 R 2 star. Now, what will all of this do? Because R 1 already we know is given by this and R 2 is given by this. So, this minus and complex conjugate would probably help us simplify things. Okay? But we make this observation that H 1 and H 2 is known. So, there is a channel estimator which tells us the channel gains, and of course, H 1 and H 2 are complex. So, now if you plug in the values of R 1 and R 2, let us see what we get for R 1 tilde and R 2 tilde. So, R 1 tilde is, if you do the math and it is not too complicated, you get H 1 absolute value squared plus H 2 absolute value squared into S 1 plus H 1 star N 1 plus H 2 N 2 star, and similarly R 2 tilde has a expression available for it. So, what does it buy us? Well, the first interesting observation is R 1 depends only on S 1. Earlier, if you note, everything was coupled. The received signal clearly depended on S 1 and S 2. Why? Both the transmitter antennas were sending together. So, it is but obvious that you will get a jumble, you will get a mixture of S 1 and S 2 multiplied by the channel gains. But I do some smart processing at the receiver and suddenly some magic happens, and this R 1 only depends on S 1. Now, we will tell you the advantage of that, and R 2 only depends on S 2. And of course, I have the estimates of H 1 and H 2, and these are nothing but some values multiplying S 1 and S 2. But this is the most interesting fallout of this mathematics that has come out. R 1 tilde depending only on S 1, R 2 tilde depending on only on S 2. This has big ramifications, because at the end my job is to guess what was transmitted, S 1 and S 2. Okay? So, we have to do a search, because this is the maximum likelihood decoding, and it is now a question of matter of reducing the search space. So, the beauty of the equation is that R1 tilde depends only on S1 and not on S2. So, the detection can be carried out only with respect to the single quantity. So, when I am going to search and find out which is the most likely symbol transmitted, I only do on the possible points in the constellation diagrams S1. Similarly, for S2, I only do search only for S2. If they were coupled, then I have to have the number of searches S1 and S2 together, and that would require me to search. If there are 64 points in the constellation diagram, then the pairs, number of pairs would be 64 into 64 as opposed to only 64. So, that is the biggest advantage that we are going to get here. The detector uses maximum likelihood decision, and so x1 tilde is nothing but, this is the maximum likelihood, R1 tilde we just now found minus this H1 absolute value squared plus H2 squared S. Similarly, x2 estimate is minimum over all the possible constellations points R2 tilde minus H1 squared plus H2 absolute value squared S. Okay. This is just the maximum likelihood ML decoding. So, that is the beauty of the Alamouti scheme. We have really reduced the complexity, the decoding complexity. Now, will it work in general? Let us consider a slightly different example. Again, we have 2 transmit antennas and 1 receive antenna. Nothing is different except that this time we employ a slightly different combining scheme, and this will lead to a mixture of the transmitted signals. So, for example, let R1 tilde be some AR1 plus BR2 complex conjugate, and R2 tilde could be some CR1 plus DR2 star plus this noise part. So, if A, B, C and D are some coefficients, then the vector R tilde can be expressed as this A, B, C, D, x1, x2 plus n1 tilde n2 tilde. So, if A matrix can be represented as A, B, C, D, then the ML decision rule can be written as x1 tilde x2 tilde is minimum over this vector x over S squared. Okay. So, now this is the process of minimizing, is a search for a vector of length 2 as opposed to a single symbol search. So, if the constellation has m points, then the computational complexity of the search is of the order m squared. If the number of transmit antennas is increased to n, the computational complexity of the search will be m raised by n. So, earlier we were only talking about 2. Therefore, I was sending symbol S1 and S2. If there were 3 transmit antennas, then the search will be over a 3 tuple. If there were n transmit antennas, then the search will be over m raised by n. So, this is the biggest problem. The complexity will forbid the use of any general arbitrarily designed scheme. This A has to be designed very carefully. But for the Alamouti scheme that we saw, this increase in complexity is avoided because of the use of an orthogonal encoding matrix. So, that was the beauty of the Alamouti code. The coding matrix was orthogonal. Okay. Therefore, it could decouple the S1 and S2. So, this is the crux. This is the reason why it is such an efficient decoding algorithm. Now, in the previous example, we have used 2 transmit antennas and 2 time periods, leading to a 2 cross 2 code matrix. Fine. This is obvious, space time. In general, we can consider a wireless system that uses n transmit antennas. Clearly, the gain with increasing the number of transmit antennas is phenomenal. So, we have again a certain number of time periods and certain number of n transmit antennas. Now, if this and the time slots is t, then we have an n cross t matrix which will represent the code. Just like when 2 transmit antennas and 2 time slots were there. So, n was 2 and time slots t were 2. So, you had a 2 cross 2 matrix. So, in general we will have this representation again, this is this epsilons dot 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 dot. So, if we look at in general, if you look at the code for this n cross t encoding matrix, then C will be written as C11, C12 to C1n, then C21, C22 to C2n, and you can keep going and you have t time slots. So, T1, Ct2 to Ctn, and if you see here we have n. So, this is the space axis and this is a time axis. Right. So, this is space and you have n and this is t. So, this gives you the n cross t. So, this is a general notation for a space time encoding matrix, okay? We can represent it. So, now the question is, what is a good space time block code? How do we design one? We need some design rules. So, we saw that a space time block code is essentially a mapping from input bits to a transmitted symbols. So, we have to play the game there. These symbols are transmitted simultaneously from the different antenna elements, okay? And therefore, they couple at the receiver. The aim of the space time decoder is to correctly guess the transmitted symbols. An error occurs when one code word is wrongly mistaken as another code word. So, suppose the wireless system uses n transmitted antennas and t time periods, then the code word we have already looked at as C1. Now, the error is set to be the decoder is set to make an error if it decides that a different code word was indeed transmitted. Okay. So, even though C1 was transmitted, we say no, it is a C2 that is sent out. So, if you now look at so, we already have a C1 which was sent out, C11, C12, so and so forth, C1n, C21, C22 up to C2n and going on for CT1, CT2 up to CTn. This one was transmitted, but what we received is C2. So, we can differentiate it as C2 11 C and so forth. As opposed to what was sent. So, I can put a superscript here and I can distinguish these two. So, this C1 was sent and this is what we decode and wrongly. So, there is an error in the decoding. So, let us look at the slides again. The probability of erroneously decoding code word C2 when code word C1 was transmitted is called the pairwise error probability. Okay. So, this is denoted by P, C1 was sent and C2 received, and this is the notation we will be using. Now, suppose the code book contains k code words. So, we can use union bind to find the upper bound on the probability of error, that the code word C1 was transmitted and erroneously decoded. And the union bound is simply the probability of error given C1 is less than all possible. So, I is equal to 2 to k, because I is equal to 1 represents the correct decoding, C1 goes to Ci. So, this pairwise error probability, the upper bound on that, will be used for our code design criteria. So, to calculate the pairwise error probability, we assume a fixed known channel matrix H. Okay. So, the average error is calculated by averaging over the distribution of H. So, for different H, we will have a different kind of a average error calculation. So, after some mathematics, we can show that the pairwise error probability is upper bounded by this expression. Okay. Now, here n of course is the number of transmit antennas, right, and we have m as the number of receive antennas. So, we have a MIMO system in place. Okay. And lambda n is equal to 1, 2, 3 up to n are the eigenvalues of the matrix A C1 comma C2. Now, what is this matrix? Let us define this. So, this matrix will play a central role in our design criteria. So, A C1 comma C2 is defined as this C2, this was a matrix, minus C1, this was the sent matrix Hermitian, into C2 minus C1. So, we define it like this. Okay. So, what is this C2 minus C1? It is like the distance, but remember what are the elements of this matrix? Well, these are symbols in the constellation diagram. So, it is nothing but a distance. So, we represent it with d. So, this is the distance between C2 and C1, 1 to 1 Hermitian, and distance between C2 and C1. So, this is the definition of this A matrix. So, and this D is the difference matrix. Now, let us talk about the rank of the matrix A, right. So, at high SNR, what we can do is you can neglect the previous equation, the denominator, and so the pairwise error probability is upper bounded by 1 over these are the eigenvalues product m, and this is the indicator for SNR. Es is energy per symbol and power noise power is denoted here and raised by Rm. M is the number of receive antennas, small r is the rank of this matrix A. So, if you recall, we had earlier said that the pairwise error probability, if represented in general as follows, some constant over GCS raised by GD, then GD is the diversity order or the diversity gain, this term diversity gain GD, and GC is of course the coding gain. All right. So, if you compare these two, we can quickly see that there is this R into M corresponding to GD, right, because S is the SNR, here S is energy per symbol over 4 n naught. So, this is an indicator for the SNR and GD is Rm. So, the diversity gain of the code GD is Rm, but what is R? R is the rank of the matrix A C1 comma C2. So, it appears that this matrix plays a critical role and we have to design this C1 such that this rank is maximized. What is M? M is the number of receive antennas. Earlier M was 1. So, in that case this diversity gain would be limited to R. Okay. Right. So, the coding gain is a function of the product of the non-zero eigenvalues of the matrix A, this one. Where is this coming from? We go back and see that this GC provides the coding gain. So, this term is essentially the coding gain, and it depends on the eigenvalues of this A matrix. Very interesting. So, the coding gain is a function of the product of the non-zero eigenvalues of the matrix A, or equivalently the determinant of the matrix A, which means that the full diversity is possible and it will be M into N if the matrix A is of full rank. So, we have to design, this essentially gives us the method to design good space time block codes. We have to design A with full rank. Coding gain we have studied earlier also, but we revisit it. So, the coding gain distance between code words is the product of the non-zero eigenvalues of the matrix A. So, we see from this expression that the block space time block codes can provide you definitely with the diversity gain and coding gain depending upon how you have designed this matrix A. So, let us now summarize this design criteria for the space time block codes. So, of course, two things played an important role, the rank and the determinant. So, we talk about the rank and the determinant criteria for designing space time block code. And what is it? In order to achieve maximum diversity, and diversity is so important in, we will take up an example to show the importance. In order to achieve maximum diversity, the matrix A should be full rank for any two code words C I not equal to C j, all right. And the smallest value of R over any pair of code words provides a diversity gain of R times M. This is called the rank criteria, M being the number of received antennas. Now, in order to maximize the coding gain, okay, so we have already talked about the diversity gain. In order to maximize the coding gain, the minimum determinant of the matrix A should be maximized for any two code words C I not equal to C j. So, this is talking about the determinant, and hence it is called the determinant criteria. So, together they are called the rank and determinant criteria for designing good space time block codes. Okay. So, we can actually do a simple computer search to look at all possible combinations, and whichever gives this high rank and maximizes the minimum determinant, right, we get that. So, let us revisit Alamouti code in this light. So, we have seen that there are two transmit antennas, right. So, n equal to 2, and the code word we have seen earlier. Now, let us consider a different pair of symbols with the corresponding code word matrix C prime, all right. So, the difference matrix is nothing but C 1 minus C prime. So, if you find out the determinant of this is given by this, and this is 0 if and only if S 1 is equal to S 1 prime and S 2 is equal to S 2 prime. In all other cases, the determinant will be non-zero. Consequently, this difference matrix D is full rank, right, when C 2 is not equal to C 1. So, that is the beauty of the design, it is a full rank. So, Alamouti code satisfies the rank criteria and gives a diversity of 2m, where m is the number of receive antennas. Earlier we had talked about m equal to 1 for Alamouti code. So, only one receive antenna. So, at least it will give a diversity gain of 2. I will just now see what do we mean by a diversity gain of 2. Is it good? Does it help? So, let us understand a little bit more about this Alamouti code. It was one of the milestones. So, maximum diversity. Since the code satisfies the rank criteria, it provides the maximum possible diversity of 2 when the number of receive antennas is 1. So, diversity gain is 2. It provides symbol decoding. So, single symbol decoding, it is simple. Each symbol can be decoded separately using a linear processing. This we have established because of its orthogonal nature. And then it is full rate, that is another interesting criteria. What do we mean by full rate? Well, we transmitted 2 symbols in two time slots, fine. So, effectively we are sending 1 symbol per time slot. So, the rate is 1. So, we are not saying that we are slowing down the communication. We did not take more time, we did not slow down the symbol rate, okay. We did not increase the decoding complexity, but at the same time we got a diversity gain of 2. So, let us quickly look at the performance of Alamouti code. So, we have made this assumption of quasi static, implying that 2 time periods are such that the channel does not change significantly. So, H value is maintained. So, let us plot the symbol error probability versus the SNR for n is equal to 2 transmit antennas and m is equal to 1 receive antenna. So, we had already studied this scheme in detail, this Alamouti scheme, and let us see how the symbol error probability curve looks like. Okay. But how do we compare? Did we gain anything? So, we consider the case when it was a single antenna system. So, n is equal to 1, right. So, we plot that curve also and compare how much is Alamouti giving us. Let us say both of them are using this QPSK constellation. So, let us plot the axes. So, on the x axis we are going to plot SNR, on the y axis we will going to plot the symbol error rate. Okay. So, if you do so, if you see the top curve is the single antenna transmit antenna and single receive antenna case. The second curve is the Alamouti scheme, both employing this QPSK constellation, and if you can see that there is a shift in the slope, the gradient of this changes, indicating the diversity gain. And also please note that these two diverge, which means as we go at a higher SNR regime, the diversity gain increases. So, it brings home to a very interesting point that the diversity gain becomes more and more effective as we go to higher and higher SNRs. Therefore, if you are working with systems which inherently work in low SNR scenarios, it is really not worth it to look at schemes that provide diversity. Diversity gain is best employed when reasonably good SNR is available. Okay. So, from the figure we observe that the symbol error probability decreases as s raised to the power minus 2, where s is the SNR, which confirms that the diversity gain is of the order 2, and the effect of the diversity gains becomes more pronounced at higher SNRs, and it is evident because the performance gap widens as the SNR increases. And if you look at the slopes of the two curves, all right, you will see that the slope is an indicator of the diversity gain that we get, and typically asymptotically you can see. Now, just a few more comments about the single symbol decoding, and then we will try to explain intuitively why diversity happens, why the diversity gain is happening. So, we have talked about this Alamouti code, and the optimal decisions can be made based on symbol at a time. And what we have is this R1 R2 star pair can be simply written as S1 S2 times omega. What is that? Well, omega is this H matrix H1 H2, right, N1 N2. So, we have just repositioned these parameters and we have rewritten the received pair as follows. So, if you see, we have this R1 R2 star that we had rewritten, and if you multiply it with the Hermitian of this omega, then you simply get H1 absolute value squared plus H2 absolute value squared times S1 S2 n. So, you can see that upon multiplying both sides with this omega h Hermitian, you decouple the decoding part. So, it is effectively two separate equations that can be solved separately. Okay? So, that is the reason why it is a single symbol decoding. Now, let us spend just 2 more minutes on why there is diversity gain intuitively. Mathematics we saw, slope of the curve we saw, simulation results we saw, but intuitively why are we getting? What is the physical reason? Can we link this mathematics to a physical intuition? So, let us suppose that instead of 2 antennas there was only one, then the received signal would depend only on the h, the fading coefficient, which can vary drastically. And what does h do? When the fading is bad, the value of h is small, so h squared is even small, right, and then the noise will dominate because the signal is just out of the picture. But if we have 2 transmit antennas, the received signal depends, as we have seen, on h1 squared plus h2 squared. We have seen this before here. See, the received signal pair depends on h1 squared absolute value and h2 absolute value squared, right. Now, when will the system be dominated by noise? Here is the noise. The system here would be dominated by noise if both H1 and H2 are small. Only then the signal will become insignificant with respect to noise and the system becomes dominated by noise. Both of them, not only both of them must simultaneously be small. If one is small, the other is large, then the signal is still there. Both of them must simultaneously drop down, but that is bad because H1 is for channel 1, H2 is for channel 2, and somewhere we said these guys are supposed to be independent, they are independently fading. So, the probability that both H1 and H2 are together simultaneously very small is very rare, and that is where we are getting the diversity gain. So, if noise must dominate, then H1 and H2 must be fading at the same time, but it is contrary to our assumption that H1 and H2 are fading independently. This intuitively the received signal is less likely to be in fade because of the diversity provided by the 2 independently fading channels. So, thus we have argued purely based on intuition why a system with 2 transmit antennas provides diversity. Okay. So, there is a very physical feel to the whole thing. So, let us summarize what we have learned today. We have introduced this concept of space time codes and we brought it out with the help of this wonderful coding scheme called Alamouti Code. We looked at why Alamouti Code works, and we also looked at this rank and determinant criteria for designing good space time block codes. Then we spent some time talking about diversity and intuitively explained why diversity happens in this multi antenna systems. We also had some examples. So, with that we come to the end of this lecture.